Namaskar. Welcome to Prakash on Basics. I'm Prakash Zog, and we've been talking of science, but we did talk and finish off what was associated with light. So we need to move ahead. Um, in coming months, I would be talking on things like the universe and radioactivity and very small particles, which are typically known as elementary particles, and molecules, and so many things. Um, in all these and in many other fields, we need to compare things. We need to what is technically known as quantify things. There is a major difference in the way in which science and some of the areas and arts, uh, art faculties deal with this process of quantification. Um, in arts, we use superlatives: um, good, better, best, um, large, huge, humongous, or we could have small and minute and minuscule and microscopic and so forth. Uh, all these are words that you have to know, and you should be able to associate them with sizes of different things. But for many other areas, comparison is through maths. It could be in terms of numbers, it could be in terms of fractions, it could be in terms of ratios, it could be in terms of powers of 10, or squares and cubes and so forth. Mm. Some things we just can't add numbers to them, or we cannot quantify them. For example, I cannot say Madhubala was 2.7 times more beautiful than Meena Kumari, for example. Or I could not say that A is 3.22 times smarter than B. Uh, or when my uncle died and I was 5% sad as compared to when my other relative died, and so forth. So when I'm happy or when I'm talking of emotions, I cannot attach numbers to them. uh, so how do we go about? As of now, let us keep all these emotional aspects and things to which numbers cannot be attached to the side. Let us concentrate on things that can be exactly measured and what is known as quantified. There were different methods of writing numbers and so forth right from the beginning. Um, Writing numbers in their decimal form and giving them special names for very large values was done by Indian mathematicians as far back as second century BC, and those texts are actually available. Um, the West use cumbersome Roman numerals, very difficult to mathematically operate on. Then they adopted the decimal system, uh, zero, etc., and they called it the Arabic numericals, or Arabic numerals. But they themselves, the Arab numerals, were in fact taken from the great Indian mathematicians who had passed on the knowledge gradually towards the West. So today, this is an accepted fact. Um, there are two aspects. How do we write large numbers? That is the first part. And understanding really how big or how small these numbers are is the second aspect. Let us try and deal with the first part today. Talking of scientific areas, and whether it is the west or the east, or the central part of the world, we tend to use uh, powers of 10 to number and name things. We talk in terms of 10 And when you talk of thousand, it gets multiplied by one followed by three zeros, and a million is multiplying by one followed by six zeros, and a billion is one followed by nine zeros, and trillion is one followed by 12 zeros, and so forth. So this is the method that is commonly used quite a few places. In India, of course, there is a different pattern that is used, which is based on terms that are given specifically to all these multiples, but are based on Sanskrit words. Um, I'll refer to, let's say, the Hindi version, which talks of saw, which is 100, and hazar, which is 1000, and lakh, which is 10 raised to 5, or 1 followed by 5 zeros, and karod, which is 1 followed by 7 zeros, and Arab, which is 1 followed by 9 zeros, and so forth. It depends upon the number of zeros that are added, or the number of place values that you have to the number itself. But then, as I said, in India, the numbers went far beyond this also. There was the curve, which was a number, let's say 5 multiplied by 1 followed by 10 zeros, and Nikharva, where there were 11 zeros after a particular number, or 11 digits, and Mahapadma, which had 12 digits. Uh, Shanku, which had 13 digits, Jaladhi, which had 14 digits, Antya, which had 15 digits, and Parardha, which had 1 followed by 17 zeros as the place value. They didn't stop there. These were all talked of sometime or the other, but there were many others in between. Uh, there was this Bahulam, which is 1 followed by 23 more numbers, and Tailakshanam, which is 1 followed by 53 more numbers. So you can imagine the number of quantities that were being thought of, mathematically operated of, and identified specifically in the mathematical texts in India. Um, Non-science areas still use uh, numbers which are relatively small, and these are associated with the ones that I just mentioned prior. I'll mention them again, but it depends upon the number of zeros or the place values that take place after one. Thousand, as I said, has three digits or three numbers. Million has six. Billion, no decimal places right now. Billion has six, and trillion has 12, and quadrillion has 15, and quintillion has 18. But these are all later developments. Sextillion is 21, and septillion is 24, and octillion is 27. As time passed, they started inventing more and more better numbers. And you must have heard of the two very large numbers that we talk of. One is the Gogol, which is 1 followed by 100 zeros. And then they thought of one more number, which was known as Gogoplex, which is 10 raised to 10 raised to 100. That means 10 raised to the power of Gogol. That means 1 followed by Gogol number of zeros. That's what all that means, let's not talk of right now. But then identification of this sort was possible. Science kept on improving, and there were many physical quantities that were being measured. And these were many a times very large or very small also. So naturally, for mass, length, time, charge, power, voltage, current, etc., number of moles, and so forth, all such multiples of numbers started being used. Um, there was a development which I'm not going into details right now, but a system was developed which is known as the System International, which is known as the SI system. And now this SI system is accepted worldwide, everywhere. There are some countries which tend to keep things a little different, But let's not let's not go into those. All scientific words then needed very large numbers. So what they did was they started using a prefix to represent the powers of 10, and this became a very common practice with time. These prefixes are given names based on the powers of 10, or how many times, or if a number is multiplied by 1 followed by 1 0, 1 followed by 2 zeros, 1 followed by 3 zeros, and so forth. So 1 multiplied by 10, 1 multiplied by 100, 1 multiplied by 1000. So 1 2 3 zeros and so forth. So there were a lot of names of this sort that were put. I'll just remind you of them. So what you have is the base unit, whichever physical quantity you are trying to measure, and then when you attach a prefix deca, it means you multiply it by 10, or 10 raised to 1 0, 10 raised to 1. Hecto is 10 raised to 2. This is the number by which you will multiply the quantity. Kilo is multiplying it by 1000. Mega is multiplying it by 6. Giga is multiplying it by 9. Tera is multiplying it by 12. Peta is multiplying it by 15. Exa is multiplying it by 18. And Zelta is multiplying it by 21. And Yota is multiplying it by 24. Um, and what about if it is 1/10 and 100th and 1000 and that type? So if it is 1/10, it was given a prefix deci. Then you have centi, like centimeter. And if it was 1,000th of a meter, it was 1 millimeter. And if it was a millionth of a meter, it was a micrometer. And remember, we talked of the nanometer when we talked of wavelengths. And then there was picometer we talked of when we talked of picofarads. That was when we talk of capacitance and so forth. Then there is a still smaller unit known as femto, which is 10 raised to minus 15. That means 1 divided by 1 followed by 15 zeros. When you start talking of size of nuclei, you start using these units. And there is also an atto, which is 10 raised to minus 19. 1 upon 1 followed by 18 zeros. I'm just giving you these names. You should have heard them sometime or the other. And this is the way in which they were talked of. Actually, we must realize that with time, larger and larger numbers were required, either to make measurements in space or in very small quantities. So new prefixes were added. All these that I talked of were not there all along. For example, giga, like gigawatts and so forth, or terawatts and so forth, both representing 10 raised to 9 and 10 raised to 12. These were adapted in 1960. Peta and Exa, that is 10 raised to 15 and 10 raised to 18, were adapted in 1975. Femto and Otto, the small ones that I talked of, were adopted in 1964, and so forth. So as time passed, they started adopting more and better different types of multiples or prefixes to a number to understand them better, rather than writing all that cumbersome big number. So what happens is you use this prefix uh, and follow it up by the corresponding unit, and then the meaning becomes very simple. For example, length is measured in terms of the SI unit for length is meter. The SI unit for mass is kilogram, and power is watt, for example. So what you do is you use, when I say kilometer, kilo is 10 raised to 3, that means 1000. So you multiply a meter by 1000. So 1000 meters will make 1 kilometer. And when I talk of 1,000 grams, I call it as 1 kilogram. And when I talk of 1,000 watts, I call it as 1 kilowatt. And when I talk of 1,000 calories, I talk of 1 kilocalorie. And when I measure quantity of matter, 1 mole, if I multiply it by 1,000, what I get is kilomole. When you look at those food packets and all that, you will find these all these words. So many kilojoules or so many kilocalories can be obtained from so many grams of material and so forth. Uh, there could be also certain multiples um, which are not really very common, and they may not be very commonly used by people. The ones that I talked of just now are the ones that are commonly talked of. But then there is another problem. If the number starts becoming really very big, how do you how do you write it down, and how do you simplify things if required? So for this, science developed a technique which is to use what is known as standard form. So many numbers were written in what is known as standard form. You write one digit, follow it up by a decimal point, put two more digits, and then multiply it by 10 raised to x, where x is the number of zeros that can be added. This makes the whole number writing process itself very small and more easy to understand and interpret. Uh, Sometimes what happens is after the decimal point, there could be 5, 6, 7, 8, 9 digits. But then there are so many that their importance in the actual calculation becomes insignificant after two places, because that is less than 1%. And so these are usually dropped off, and therefore only the single digit followed by a decimal point and two more digits is usually talked off in its standard form, because the rest of them are really insignificant. Um, let's try and understand this, because I've been talking and it could get a little complicated. Um, Science developed a lot of techniques to measure things very accurately, and the velocity of light, something that we talked of long back, was actually very accurately measured in vacuum, and it was found to be 299,792,458 meters per second. Now, every time I have to use, and this is standard notation, which is C. Now, every time if I start using this big number, first of all, trying to remember it is going to be difficult, and using it in calculations could also be pretty troublesome. So, what do? You try and reduce it down to its standard form. Let's try and understand this. I have actually put down this number on behind me, and I hope you can uh, read it as I go through it. The number, as I said, is C. The velocity of light is 299,792,458 meters per second. 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. Pretty troublesome. So what do? You start reducing the numbers to its closest place, which is easy to understand. Anything up to 5 is taken as 0, and anything from 5 to 9 is taken as 10. So this 8 is as good as 10. So this 58 effectively is as good as very close to 60. So you have 6 here, and 4 and 6. 6 is as good as making this as 5. if if this is 5, it is not higher than 6, so you forget it and treat this as 2 remaining as it is. And all these places, 1, 2, 3, 4, all these are 0, 0, 0, 0. This is 9. So 9 is as good as 10. So this becomes 8, 0, 0, 0, 0, 0, 0. And if this is 8 and this is 9, as good as 97, which is close to its 100 value, and this is as good as 99 is as good as 100. And if 100 means the next digit here. So what effectively the whole thing boils down is 3, 0, 0, 0, 0, 0, 0, 0, 0. Because all these numbers after 299 are as good as very close to 300, and the rest of them can be treated as 0. So now what I have is a number which can then be written as 3 multiplied by 1 followed by 8 zeros. So I have 3, 1, 2, 3, 4, 5, 6, 7, 8 zeros. And now I write it as 3 into 10 raised to 8 meters per second for all my calculations. So the number becomes small. This is now a standard form. Ideally, standard form will be 3.00 into 10 raised to 8 meters per second. So now I have reduced down the number to a very simple form and easy to write. There are many more numbers that could be equally complicated. I'm just talking of, I've written one or two here. This is mass of Earth. Mass of Earth is 5.97219 into 10 raised to 24 kilograms. But after the third place, the rest of the numbers are very insignificant. They hardly make any difference in the calculation. So I can skip all these three numbers. And if I skip these three, this is 2. So it's not going to make a difference in this. So it is going to become 97 here. So 5.97 into 10 raised to 24. So what do? I write it down as 5.97 and multiplied by 1 followed by 24 zeros. So many kilograms is the mass of Earth. Troublesome. What about the mass of the Sun? The mass of the Sun is 1.9891 into 10 raised to 30 kilograms. Now, this 98 will make it 99 here, and 99 will make it as 2 instead of 1.99. So I can reduce it down to 2 into 10 raised to 30. And this is as good as 6 into 10 raised to 24. Now see how things have become simple. So I have 2 into 10 raised to 30 divided by 6 into 10 raised to 24. And that's something that I can do mentally also. 30 minus 24 will give me 6. So there will be 6 zeros on top. And 2 upon 6 will make it 1/3. Which means the 1/3 is 0.33. That and 10 raised to 6 is million. I just told you some time back. That means the mass of the Sun is a million times, but 1/3 of that, 1/3 of a million is 3.3333 into 10 raised to 5. Or if you talk in Indian numbers, it is 3.3 lakh times more. So the mass of the Sun is 3.3 lakh times more than the mass of Earth. Start dividing these two and trying to find out numbers, it's going to get more difficult. So that's why the standard form becomes more simple and easy to use. And what about numbers that are smaller? So if I'm talking of 1 divided by 10, I multiplied by 10 raised to minus 1. If it is 1 divided by 100, I multiplied by 10 raised to minus 2. If it is 1 divided by 1000, I multiplied by 10 raised to minus 3. Remember, long back when we talked of electricity, I told you as a number the charge of an electron. The charge of an electron is negative, of course. I had given you only 1.6 into 10 raised to minus 19, but the actual number is minus 1.60217663 into 10 raised to minus 19 coulomb. So suppose a student is supposed to write this down. What will he do? He will write minus 0 point, then 18 zeros, and then 160217663. It's very troublesome. So what does he do? He makes the whole thing pretty simple. He converts it into standard form. So he separates out that 10 raised, all those decimal places, he shifts back and makes it 10 raised to minus 19. And shifting all that has brought him to 1.6 into 10 raised to minus 19 coulomb. Now things are very easy for him to calculate. So things have become much simpler. So simplifying the things in this manner, writing numbers in either powers of when they are positive, it means the number is more than 1. If it is negative, it means the number is less than 1. And it could be any amount smaller. It could be extremely small or extremely large. There's a small hitch in this. In specialized areas, some odd different units are still used, irrespective of this technique. Uh, we could have Fermi, which is used to measure the size of the nucleus of a particular atom, or angstrom, which is used for measurement of size of atoms, of wavelengths. Um, you could use light years to measure distance, which is very large. You could use AU. AU is a unit that is astronomical unit that is used to measure distances, keeping taking distance of Earth to Sun as one unit, and then writing everything in multiples of that. And there is another beautiful one which is known as parsec. I'll talk of these when we start talking of stars and planets and other things. So these are all specialized units. There could be things like electron volt or million electron volt, and there are some very complicated ones, which is known as uh, Planck length and Planck time. When you start talking of the origin of the universe, how Big Bang and all that started. So there, time and lengths are measured in terms of Planck length and so forth. So there could be many complicated things. I'm just telling you this because we are not going to use them in practical life. We are going to use, but we should know where are we finally leading to all this. But what's the use of all this that I'm talking of? One, very complicated big numbers like this can be simplified. That's the first step. Second step, making calculations uh, would be pretty simple. As just as I told you that you, if you have to find out the ratio of mass of Earth upon mass of rather mass of Sun upon mass of Earth and get the ratio, I could be able to get ratios in this manner. They could be pretty complicated numbers. Uh, Let me harass you by giving you a set of numbers. Okay, there is a constant known as Rydberg constant. I'm just listen. Uh, there is a Rydberg constant. Rydberg constant's value is um, 1.097 into 10 to 7 per meter. That's its numerical value. But what's its formula? Its formula is R is equal to m e fourth upon 8 epsilon naught squared h cube c, where m is the mass of electron, which is 9.1 into 10 to minus 31 kilograms. That E is the charge of an electron, which is this particular number that we know, the one that I told you, 1.6 into 10 raised to minus 19. So I have to take it to the power of 4 because it is E fourth. And then epsilon naught is permittivity of free space, which is 8.85 into 10 raised to minus 12. I have to take the square of that. And h is Planck's constant, which is 6.63 into 10 raised to minus 34. And I have to cube that. And c is velocity of light, which is 3 into 10 raised to 8 meters per second. Think of the amount of calculations that are going to work out. 9.1 into 10 raised to minus 31 into 1.6 into 1.6 into 1.6 into 1.6 into 10 raised to minus 19 into 19 into 19. If I write all that, it might appear troublesome, but you can take all the powers out separately and keep only the simple single numbers together. And then calculations become very simple. And then even a simple ordinary calculator will give you the answer of 1.097 into 10 raised to 7, because 10 raised to 7 will be number that will come out. So a very complicated mathematical operation can be simplified by using this standard form. And so everywhere, when you talk of economics, we talk in terms of millions and billions and trillions and so forth. When we talk of population of India, we talk of population of 1.5 billion. And when we talk of the population of Earth, we talk of 1.8 billion and so forth. And when we talk of rich people, we talk of the money that they have in terms of millions or billions of rupees or dollars and so forth. And when we start talking of very small things, like plastic sheets or the plastic bags that we use, we talk of microns, which is a micron is a micrometer. And when we start measuring things, it could be in threads and other things, it could be in terms of millimeters. And small distances are in centimeters, and bigger ones are in terms of meters and kilometers and so forth. So using these multiples has become a part and parcel of our life. We use, if you are measuring very large masses, you talk in terms of tons, or we talk in terms of kilograms, or we talk in terms of grams or milligrams or milliliters and liters and kiloliters and so forth. So using these multiples helps us to understand how writing and multiplying numbers takes place. This is the simplified version. If you have liked whatever I have said, please like and subscribe to this channel. um, Tell your friends about it. Whenever you look at numbers and figures in so many newspapers and so many places, try and make sense of what the suffixes and the prefixes attached to them really mean, how they are used in languages and how they are used in sciences. That leaves us with one more aspect. These are numbers, they are big and small, but how big are they really? How small are they? We don't really, when I talk of 10 raised to minus 31, and when I talk of 10 raised to 7 and 10 raised to 24 and all these numbers, 10 raised to 8, what does it really mean? Do I really get a sense of how big or how small they are? Many a times, no. Trying to make sense of these numbers is our next step, and that we'll do next time. Till then, namaskar.